Okay, so on number 1 it says the function f is continuous on the closed interval from 2 to 14 and has values as shown in the table above. Using these subintervals, what is the approximation of this integral using a right Riemann sum? So what are you going to do? Okay, so you're going to multiply what by what? The width times the right hand height. Yeah? So 3 times 28. And then plus what? Times 5 times 34. And then 4 times 30. Okay, whichever one that is. That's 150, 100, so 170. That's 120, that's 290. 3 times 20 is 60. 3 times 8 is, so 78. No, 3 times 8 is 24. So 84, right? So 290 plus 84, 374. Okay. So what about finding this integral using trapezoidal? So let's just write out the formula. Okay, so 1/2 what? Yeah, 1/2 what? Yep. Okay, so 1/2 3. 10 plus 30 plus times. Okay, plus 1/2 1. Okay, so that is 40 divided by 2 is 20, so 60. That cancels out, so it's plus 70, and then that's 60 divided by 2, so 30, so 160. Okay, so let's talk about 3. The data for the acceleration of a car from 0 to 6 seconds are given in the table above. If the velocity at time 0 is 11, the approximate value of the velocity at time 6, computing using a left Riemann sum with 3 subintervals of equal length, is. So they give me that velocity at time 0 is 11, yeah? And they want to know velocity at time 6, given acceleration values. So what are you supposed to be doing? Okay. Mm-hmm. Mm-hmm. So initial plus change equals final. And then they say you do this using left Riemann sum. So then 11 plus 2 times 5, width times height, 2 times 2, 2 times 8. We good? Okay. So 2 times 2 is 4, 2 times 8 is 16. That's 20, 30, 41. Okay. Number 4. A table of values for a continuous function at the 4 sub. What is the trapezoidal approximation? So are we good with doing that? Do we need to? Okay. Let's move on. We can just skip number 5. Don't worry about it. Okay. If a trapezoidal sum over-approximates the integral from 0 to 4 of f of x, and a right Riemann sum under-approximates, which one could be the graph of f? So what do you think is the way to do this? You know what I would do? I would just take these and draw a trapezoid from like here to there, because no matter if I do small trapezoids, it's a little bit harder to see, but if I do one big trapezoid, does the trapezoid over or under? Over. Trapezoid over or under? Okay. Over or under? over or under, and then the same. Okay. And then a right Riemann sum under approximates. Well, a right Riemann sum uses the height at the right hand, right? So is that an over or an under? Under, whereas the right hand right here would be an over. So it's got to be A. Okay. You're only having to work those. Okay, so it says the volume of a spherical hot balloon expands as the air inside the balloon is heated. The radius of the balloon in feet is modeled by a twice differentiable function r of time t, where t is measured in minutes. For 0 to 12, the graph of r is concave down. The table above gives selected values of the rate of change of r. The rate of change, r prime, and the radius of the balloon over the time interval from 0 to 12. The radius of the balloon is 30 feet when time equals 5. So, C. Use a right Riemann sum with 5 subintervals indicated by the data in the table to approximate the integral from 0 to 12 of r prime. Using correct units, explain the meaning. Okay, so first let's just figure this out. It says using a right Riemann sum. So what would you write down? Okay, so 2 times 4 plus 3 times 2, 2 and 1.2, 4 times 0.3, and then 1 times 0.5. Okay, so that is the value of it. As far as explaining the meaning, what does that find? So let's make sure we understand what's going on. The volume of spheres expands. Okay. R prime is the rate of change of the radius of the balloon. So if this is the rate of change of the radius of the balloon, then this is how much the radius has changed, has increased, right? Exactly. So that's what I would say. The radius of the balloon has increased, or you could say changed, I might say the amount, so I don't have to actually quote that number. The amount the radius of the balloon has increased or changed in, so we talked about what it is. In what? Okay, so that's the time, and what's the unit? In feet over these 12 minutes. Okay, good. D. Is your approximation in part C greater than or less than the actual integral? So if I let this whole number equal, let's say, little a, then is little a greater than or less than the integral from 0 to 12? Okay. How do I know whether or not a right Riemann sum is going to be an over or underestimate? Remember that we just looked at 5 graphs and we were like, okay, a right Riemann sum would be an over, or it would be an under. What determined whether or not it was over and under? Okay. Okay. Does it also have to do with, let's see. So R prime is decreasing, right? But the graph of R is concave down? If it's decreasing, let's see, then a right Riemann sum would be. But if it's decreasing, wouldn't a right Riemann sum be an under approximate? Yeah. Yeah, that's what I'm going to go with. Because, well, do I know? Do I know for sure? Yeah. The volume expands there. Okay, the rate is getting smaller. Okay, R. Because R is concave. The only reason I just, like, that made sense to me, right? But my problem was I didn't know that it was for sure decreasing the whole time. But if R is concave down, doesn't that mean that R prime is strictly decreasing? Because of our fun chart? Does that make sense? Okay. So I know, so I can say, because R is concave down, R prime is decreasing. Therefore, a right Riemann sum, a right hand Rm, right? Rm would be an underestimate. Okay, good. Okay, let's do this one. A test plane flies in a straight line with a positive velocity v of t in miles per minute at time t minutes, where v is the differentiable function of t. Selected values of v of t from 0 to 40 are shown in the table above. Use a midpoint Riemann sum with 4 subintervals of equal length and values from the table to approximate the integral from 0 to 40 of velocity. So let's go ahead and do that first. So the integral from 0 to 40 of v of t is approximately, how do we do midpoint? I have to skip the middle term, skip 1, and then use that as the height. So the width is 10, but the height is the height at the midpoint. Does that make sense? So it's 10 times 9.2 plus, what's the width? Another 10 times the height of the midpoint, which is 7. Are they all 10? Then I'm going to say 10 times 9.2 plus the midpoint height, 7, plus the midpoint height, 2.4, plus the midpoint height, 4.3. And there we go. Okay. So whatever the value that happens to be, what would that unit be? If this is the integral of velocity, what are you finding? Miles. Okay. So it says, show the computations lead to your answer using correct units. Explain the meaning of the integral from 0 to 40 of v of t in terms of the plane's flight. Remember how we say, like, the integral, like, initial plus change, and the integral is the change? So this is the change. The change in what? Okay, so I would say this is the change in position of the plane, or the plane has flown this many miles. Because it always has a positive velocity, right? If it always has a positive velocity, then this is actually the same thing as total distance traveled. Because the velocity never goes negative, right? So this is the total distance traveled by the plane over these 40 minutes. Why didn't I put a unit in here? Exactly, I already put it right there. Okay, we good? Okay. Find a trapezoidal approximation for this integral. So from -3 to 15 of f of t dt using 6 subintervals, where the change in t is 3. So we're talking like here, here, all of these, right? So how do I estimate the integral from -3 to 15? Okay, so let's do the trapezoid, yeah? So what's the area of this trapezoid? Like, this is my base, right? That's 3, height 1, height 2. What's height 1? So 1/2 base is 3, height is -1, height 2 is 0, right? Okay, plus this right here. What would you say about that trapezoid? It's the same, only it's, okay, it's +1, so 1/2 base, height 1 plus height 2. So don't those just kind of cancel each other out? Okay, plus 1/2 base, which is 3, plus height 1. Okay, what would you say about this trapezoid compared to that trapezoid? So can I just say times 2 on that one? And then the other two will cancel? Okay. Okay, so it's really just this right here, which is 3 times 4, which is 12. Okay. That's easy enough. Approximate the average temperature in degrees Celsius of the water over the time interval from 0 to 15 days by using a trapezoidal approximation with subintervals of length 3 days. So this gives you the temperature in degrees Celsius, and this says find the average temperature. So is this an average rate of change or an average value? Yeah, because it gives us temperature, and then it says find the average temperature. So what do you write? How do you find average value? Yeah, this is an average value. So it's 1 over 15 minus 0 times the integral from 0 to 15 of WT. Now, there was a clue that we had to do the integral because it said use a trapezoidal approximation. You never do that to try to find slope. You're just trying to find area there. So it's 1/15 times trapezoid 3 times 20 plus 31, right? And then 3 times 31 plus 28. We good? Can we go on? Okay. Okay, let's just talk about this one. We don't have to necessarily. Okay, let's just say what it is. Okay, use a midpoint Riemann sum with 4 subintervals of 4 subdivisions of equal length to approximate the integral from 0 to 24 of r of t. So midpoint, 4 subdivisions, right? So that means you're going to go from 0 to what? 0 to 6, use the height at 3. 6 to 12, use the height at 9, and not 12 to 18, height at 15, 18 to 24, height at 21, yeah? Okay, so there we go. And it says, using correct units, explain the meaning of your answer in terms of water flow. So here's what I've got. The rate at which water flows out of a pipe in gallons per hour is given by the differentiable function r of time t. So when you find the integral of r, when you find the integral of gallons per hour, what are you finding? So the change in gallons, right? Okay, so you could say the change in gallons, or the amount of, so if this is a rate, if you integrate a rate, what do you get? The amount. So let's say the amount. And I'm going to go ahead and assume, well, I can't really assume, but it doesn't seem like this is a situation where all of a sudden it would, like the water would flow back, you know what I mean? So So it seems like gallons per hour is always going to be a positive rate, which means you could say the total amount of water that flows out of the pipe. Does that make sense? Total amount of water that flowed out of the pipe in gallons from time equals 0 to time equals 24. Okay.